So in my last posting, I showed how this integral here, that's something that Facebook has kind of been bragging about, that one of their neural net AIs can solve, can be solved using free software tool Axiom. Most importantly, they can just do the integral and this gives you this solution here. And this is the solution Axiom gives you. And then Sage, and I ran through how to, Sage couldn't just do the integral with an integrate command, but I was able to step through kind of the Risch algorithm, but I didn't really go into detail about really what Robert Risch is most known for, and that is the Risch Theorem. So that's what I want to do now, is just run through this again, and this time really show how to use Robert Risch's theorem. So this is the integral we're trying to solve, this one here. So how do we do this? Just run through this again. We set up a function field over the algebraic field q bar. We have a root. We have the root already defined in the numerator. This is the two parts, the top and the bottom, the numerator and the denominator of this expression here. We got the numerator and the denominator. So what do we do here? We construct, I call it k. Yes, we construct an extension field k. We restrict by y squared minus the root, which makes y equal to the square root of the root. We define now the integrand, which is the numerator put into the correct ring R, divided by y, which is the root. It's the numerator over the root, as we can see. The integrand, numerator over y times the differential of x. And then we construct the divisor of the integral, the integrand, and it is this. We then construct the polar, we extract the polar part of the divisor. It's this, it's the poles of the divisor. We construct completions, which are series expansions at each of the poles. We then, what do we do next? We, then for each completion, we actually construct the series expansion of our integrand times the dx, and we get this. We look at the polar, the first order polar coefficient here. We see that we need these two bounce each other. We need a 0 at the one and a pole at the other. So we then construct this divisor, here. We see if we can find a function that on the curve that matches the divisor. We can't. We try again with larger and larger divisors until we eventually find our solution. Alright, so what does all this mean? Let's go to the end here. Okay, so algebraic geometry, you can come into it in a couple different ways, and probably the most common way is to look at it as just a generalization of systems of equations. So I have x squared plus y squared plus z squared equals 1, or our sphere, but then I might have something x to the 5th minus 17z to the 9th plus y equals 14, and who knows what this is, some higher power, 9th degree surface here, and then maybe I'm going to intersect it with, I don't know, it's these two. This will give me a sphere and a plane. But these two alone just give me a surface. And I look at these and I want to know what are the simultaneous solutions of these equations in x, y, z space. And that's probably the most common way to approach algebraic geometry. We just have a system of polynomial equations, and however many variables you want, and just as x squared plus y squared equals 1 is the equation of a circle, unit circle centered around the x-axis, centered on the origin here, and this is the equations of some more complicated thing that we're looking to find what the solution sets are that match up with x, y, and z. However, as I've gotten further into the Risch differential algebra and the Risch theory, I found that there's a different way. It's a different generalization. It's a different way you can kind of head into algebraic geometry, and that is to consider we want to do something like this. We want to take, I don't know, let's just say x to the 4th plus 1 dx. We're trying to simplify this integral. And the way I'm going to simplify this integral is I'm going to introduce, first of all, a polynomial equation, y squared equals x to the 4th plus 1. So y is then the square root of x to the 4th plus 1. And this integral transforms and becomes 1 over y dx. And we now want to ask ourselves, how can we find solutions to this integral subject to this condition? One of the things I like about this approach is that you immediately start looking at functions and differentials on the algebraic curve. This thing, you can graph this at least real version of this graph. This is going to be the the square root of x to the 4th plus 1. So it's going to be what's it going to be? It's going to be something like x to the 4th plus 1, something like this. Something shaped like this, roughly. But we can immediately start saying, okay, what is this? How is this function? This function exists on this curve. We can start asking in particular, where are its zeros? It may have a 0 here, or it's got a pole here. It goes to infinity. The function goes to infinity at this point, and goes to 0 at this point. And then, let's say if you have like a 0 or a pole that's somewhere off this curve, what does this mean? What is the role of these zeros and poles out here? And really, they mean nothing. They mean nothing, because it'd be like, what would be the meaning of this expression if y was not the square root of x to the 4th plus 1? Well, we just don't care. It is the square root of x to the 4th plus 1. So we just don't care about these things at all. We only care about the behavior of the function on this curve, on the algebraic curve. And let me just draw another curve. Very well-known, famous algebraic curve. If I can remember it, it's going to be, I think it's x. I think that's it. I think I got it right. And it looks kind of like this if you plot it. The crossing point is at the origin. And then we can say, well, if we were given a function like, I don't know, 1 over y, for example, well, this is, it's a pole at the origin here, and y becomes 0, this becomes infinite. And we can also look, so this is infinity. This is infinite. Okay, so what about something like x over y? Well, x over y on this branch of the curve is going to be 1, but on this branch of the curve, when it comes down here, it's going to be negative 1. So we can have different values of a function on the same point where the curve crosses itself. It has this self-intersection, these singularities, as we call them. So we get this kind of interesting behavior, and we really want to, we need to resolve these singularities, as they say, and that's the subject of a whole different lecture. But really what I want to say here is that just given any function, given any algebraic function, a ratio of polynomials, polynomial divided by a polynomial on an algebraic curve, we can characterize it almost completely by just looking at where are its zeros, where are its poles, identifying them, identifying their strengths, and a self-intersection point like this singularity here. We're really going to have like two separate points, like this point and this point here, that need to be separated and resolved independently of each other. But that's all built into the machinery, so to speak. So that's what a divisor is. A divisor is basically just a collection of poles and zeros. If I were to, let's say I were to consider something like x squared over x plus 1, x minus 1, perhaps. This is now not an algebraic curve. It's just a standard function defined on the real line. Maybe complex lines too, but in this case we're fine on the real line. And what do we know about this? It's got poles at 1 and -1, and it's got a 0 at infinity. Well, actually no, it doesn't have a 0 at infinity. Maybe I should have made that. It does not have a 0 at infinity, because this thing goes to infinity, it becomes 1 at infinity. It has a 0 at 0. What do I want to do here? How do I want to go about this? I want to make this I think just an x. Okay. So what's it got here? It's got a 0 at 0. So when x is 0, it's 0. When x is 1 or -1, it's a pole. We have a 0 in the denominator. And then we also have a 0 at infinity. When x goes to infinity, the denominator is dominated by the x squared, so it's like x over x squared, which is 1 over x, and we have a 0. So we can just characterize a standard rational function by its poles, and also if we wanted to, let's say if we put a square here, then this would be the +1 pole. This would be a second order pole. Second order. I'd say I'll put it squared. Not that it's really one square, but it's a second order pole at 1, and that would actually cause this to be a cubic term in the denominator as we went to infinity. So it would be a second order 0 at infinity. And we can really characterize a great deal of pretty much up to a multiplicative constant. We can completely characterize a rational function by the location and strengths of its poles and zeros. And it's exactly the same thing on an algebraic curve. That's what we've got here. It's a little bit different because it's a differential and not a function. It changes it around a little bit. You do have to pay attention to this, but really that's what this is. This is just telling us where are the poles and the zeros on our algebraic curve. And then to find the logarithmic terms in our integral, we want to look at the poles in the integrand, and that's what we've got here. We do this calculation, we kind of reassign strengths based on the coefficients of these polar components here, and then we want to look and see if can we find a function that has this particular configuration, a 0 here and a pole here. And if we can't do it, then we want to go to a second. Can we do it for second order? Can we do it for third order? Can we do it for fourth order? And here we got to fourth order and we stopped and we found the solution. But we really want to know. This could be 104. It could be 1004, or it could be impossible. It could just be that you just keep going and you don't get anything. So how do you know when to stop? And that's the question that Robert Risch was able to answer back in the 1960s, late 1960s. Basically what happened with algebraic geometry was that in the mid 20th century, algebraic geometers really tried to lose any kind of dependence on the complex number field for their base field of operations. They'd been very successful in analyzing rational functions, algebraic curves over the complex numbers, but in the mid 20th century there was a big push to lose their dependence on that and work over arbitrary fields. So what you have here is you're given some algebraic curve C. We can construct something called the Jacobian variety. I'll call it J. I'm going to write this as a dotted line because it's not a homomorphism. What it is for every function, for a function on C, for a function here, put it up here a little bit. For a function on C, it actually maps through to a divisor on J, or I should say a point. Word this. F, you construct its divisor, and that gives you a point. It is actually a point on J, and that is one of the characteristics of this Jacobian variety. There are the points on the Jacobian variety correspond to the divisor class groups. Basically, all the divisors, there's a collection. A divisor is a collection of poles and zeros and their strengths. So, pole at various locations on the algebraic curve, something like this, and maybe a second order zero at I don't know, something like this. It's kind of a wild example, but that's what a divisor is. It's just a collection of poles and zeros, and all the divisors that correspond to actual functions are part of a single class group. And then there's a lot of divisors that don't correspond to specific functions, and they're in other class groups. That basically, you think of all the divisors, it forms a group, and you mod out by the group of principal divisors, which are all the divisors that correspond to actual functions, and that gives you your divisor class group. Divisor class group. Divisor group, mod, principal divisors. Principal divisors. And it turns out that these divisor class groups, the elements in the individual divisor classes, can be represented by points on an algebraic variety, an algebraic variety called J. And what's really amazing is that the divisor group operation, which is basically multiplying functions together, or add. If you were to say f squared, this was the divisor corresponding to f. F squared would be second order pole at this location. And the fourth order zero here. So multiplying functions together basically acts additively on the poles and the zeros and the divisors. And this J, this Jacobian variety, has the characteristic that not only do its points correspond to elements in the divisor classes and the divisor class groups, but this operation of multiplying functions, adding divisors, can be represented on the coordinates of J using rational functions. That it is itself an algebraic variety, and there's a group law defined on it, and this group operation is defined using rational functions, just ratios of polynomials, which is somewhat amazing, and proving it would be way beyond the scope of this lecture. But this is the structure that basically Robert Risch is working on. And then in the mid-1960s, the Japanese mathematician Shimura and Taniyama really made the first serious study of what happens when you take one of these Jacobian varieties, or any algebraic abelian variety, any algebraic variety with a group law defined by rational functions defined on it, and reduce it mod p, and what happens. And what they found was, J prime is J mod p, and what they found was there was kind of an amazing relationship between the order of the group elements here and the order of the group elements you get down here. And the relationship only held if you had good reduction, and the most important criterion for good reduction is that the genus of the curve does not change. Genus does not change, or at least the genus of C does not change. That gives you good reduction here on J. If the genus does not change, then any element in this J here, if it has a finite order, call it n, then the corresponding O of an element is n, then O of the corresponding reduced element n here is going to be n divided by some power of p, the characteristic. And once Shimura and Taniyama had discovered this and published this, Robert Risch came along, I don't know, late 60s, really published his key paper around, I think it was like 1970. And what he realized is that if we're trying to find, whether f or f squared or f cubed or f to the fourth is principal on one of these algebraic curves, what we can do is this. We can reduce this curve mod p, and we can construct its corresponding Jacobian variety, and this diagram commutes. We get the same j prime here in this direction as we went in this direction, and this calculation is basically doable. And if we do it, we can compute the order of the element here, and then what we know is that we don't exactly know n, but we do know it within a multiple of p. So we just do this for two different p's, and when we do that, we find each of the n's. Basically, we find all the terms of n that are relatively prime to one prime, and all the terms that are relatively prime to the other prime, and that's enough information to tell us what the order of the original element up here is. So how can we actually do this in Sage? Well, we just go back to, we're going to just run this whole calculation. Well, first of all, what we're going to do before we do any of this, we got to check for good reduction. So we ask what the genus is of our first, the curve we're working on, and we find that it's 3. So now we're just going to start going into different prime subfields, and we're just going to run the whole, not run the whole calculation again. We're just going to construct L, and we're going to ask, do we have good reduction? In this case, we don't. The genus changed. No good reduction. All right, try the next prime, 3. Genus is 2. Still changed, not 3. All right, let's try 5. We know that there's only a finite number of primes in which there is bad reduction. We know that this process will terminate. We know that we will get a prime without having, we can't just do this forever. And there we go. There's our first prime with good reduction. It's 7. And we need one more. So let's move on, try 11. Okay, so we got 7 and 11. So now we just basically redo this calculation on 11. I could go a little further into this, but I already know that I'm going to have a bit of a problem. And I can look back up here and I can see the problem is here. I need to characterize these two places. To build this divisor, I need to characterize these two places on the algebraic curve. And you'll see in order to do that, I need I need the square root of -1. And the question is, does the square root, I can actually look at the whole thing here. I just need 1, x and y, they're in there, they're just part of the construction. And I need a 4, I get 4s are fine. And the integers I. It's the only thing I need beyond just the integers. I need I need the square root of -1. And I could go into this thing and I can go deeper into calculation, and what I'm going to see is that I don't have a square root of -1 in either F11 or F7 because they have their form is prime FP. If P mod 4 is 3, then we have no square root of -1. But if P mod 4 is 1, square root of -1 exists in FP itself. And you'll see that 7 is of this form, and 11 is also of this form, so I don't have a square root of -1 in either of these fields. So I need to do something to get a square root of -1. And it turns out the simplest way to get a square root of -1 is to just extend the field like this. Why? Well, basically when you construct a finite field of order p to the n, all of your nth degree roots are reducible in this field. Here you got some of your roots. Some of your polynomials are reducible, some are irreducible. The polynomials, that's what I meant to say. All nth degree polynomials are reducible in this field. So what I want to extend by is a second degree polynomial to get the square root of -1, something like a squared equals -1. Second degree polynomial, I just go to Galois field 49, and I just know that I'm going to have square root of -1 in this field. So this is the field I want to go ahead and just do my calculation on. And of course I can just take the genus again. It hasn't changed. Going from 7 to 7 squared does not change the genus. And then what do we want to do here? We want to take the integrand. We just want to do the whole thing again, basically now all in a it's different. You just see that it has changed. It's been reduced modulo prime. It's different, but you notice that these two poles exist. They split apart. If I had not gone to Galois field 49, these two would have collapsed together, and that would not have been desirable. So I'm going to pull out the poles again. I'm going to go with, what should I do here? Let's do this. And basically just run this calculation again. Nothing. This calculation will always terminate in a finite field. In characteristic 0 it might not terminate, but in a finite field it will always terminate, so no, we can't just run forever. And right here we found our first answer. So we know that in GF7 squared, we know that the I call n, the order of E, is going to be 4. It's going to be 4 times 7 to some mystery power. We'll call it A. Okay, and now I can just go and I'm going to do the same thing again. I'm going to run this calculation with 121. The genus is, it doesn't change. And there it is, 4. So now we also know that in GF 11 squared, 121, the order of E is 4 times 11 to the A. And these are equal. This is equal to this. And you can look and just compare these two to each other, and you can see these are integers. The only possible way that both of these could be satisfied is that this is B. This could be a different number, but you can see they have to both be 0 powers. OD is in fact 4 in both cases, and that's it. That's the key information that Robert Risch. This is the theorem he is most famous for, is performing this analysis, extracting this information, and once we have the 4, then we can go back to the analysis we did up here, and we know now what number we need to put in here. We don't just run this forever. We know exactly where we need to go to get an answer if it exists on this algebraic curve.